Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 6 on nonparametric methods, looking for alternatives for analysis of variance, and also hypothesis testing follow-ups in ANOVA when you actually have specific comparisons you want to make rather than all possible pairs. So in previous sections, we saw one-sample tests, where the alternative to the t-test was either the sign test or the Wilcoxon sign rank test. Then we saw two-sample procedures, the Wilcoxon Mann-Whitney test, and now we're looking at when you have many populations you want to compare the means or medians between. Traditional methods would have the analysis of variance, where we assume that the the population distributions each are normal and have equal variances. So when either of those two model assumptions are not met, then we can look in this chapter, Chapter 6, for alternatives, and here our method is going to be the Kruskal-Wallis analysis of variance. So this is a nonparametric test for testing whether the medians for all the populations are equal versus the alternative that at least one pair of medians differ. And here we still have model assumptions, but instead of normality, we only need that we have identical shapes and spreads. So this is a similar model assumption as the two-sample Wilcoxon Mann-Whitney test, but in this case we have more than two samples. And the basic idea is that we're going to combine all the samples, rank all of them together, and then return the joint ranks to the individual samples and ask whether those distributions of ranks are similar between all of the samples. All right. So let me remind you, of course, that when we have highly skewed data or heavy-tailed distributions, you might first attempt a transformation to see whether you can get to normality or close to it. But there are cases when it's really hard to do that, and in that case, the Kruskal-Wallis test is there to help us out. So let's look at a fairly old data example. This is a hydrocarbon emission data for cars that are at idling, and we're going to measure those hydrocarbons in parts per million. And these are going to be on automobiles of different years of manufacture. In particular, these data were collected as a random sample among all automobiles tested at an Albuquerque shopping center. Okay, so here, I paged up for a second. So here we've got 5 groups of automobiles. We have cars that are from before 1963, then we have 63 to 67, 68 to 69, 70 to 71, and 72 to 74. All right, so we've got 5 categories of automobile, and we want to know whether the hydrocarbon emissions change over these periods of time. Okay, so I've put all the data in here. Notice I've made the data rectangular by putting in some missing values. So I have a rectangular data set, and once I read that in wide format, I'm going to use the melt function to turn it into a long data set and label the years that the data come from and the hydrocarbon values that we're going to analyze. And we can look at a summary for each year grouping of the hydrocarbons. And on the next page are those results. Here's the, hold on a second, I think something's missing. There's some output missing here. Let's see if interesting. It's there, it's just hidden. All right, Easter egg. Anyway, let's look at the just the spreads. Okay, so maybe we'll just look at the interquartile ranges over these. We have 470, 500, and then 200, 200, and 150. So it looks like the spreads are a bit different. If we plot the data, we can see some fairly big differences here. The oldest cars are at the top and the newest cars are at the bottom. You can see the hydrocarbons decreasing substantially towards zero as time goes by, even just over this 1 decade, which is encouraging. We can see, though, also that the spread of those older cars, not only are the means or medians greater, but the spread is also greater. And that's very common when you have right-skewed data and you have populations that are all right-skewed, that the larger the values are, also the more spread you get. And so we don't yet have the model assumptions met for equal shapes in this case, but once we perform a transformation, perhaps we will. I do, just to show what happens, perform a standard analysis of variance here, but I'm going to skip that because it doesn't really apply since we don't have normal data. All right, I'm going to skip that also, and I'm going to come back in a moment. All right, so here is the data, zoom out, on the log scale. And on the log scale, sorry, I'm jumping around, right there. As we compare these distributions now, we actually have a slightly larger spread on the bottom, but the difference of the spreads is not that great anymore, not what it was on the original scale. So this is a point where I would say this is probably good enough and to perform the Kruskal-Wallis test. Now some notes here. I'm paging up now. Okay, to the Kruskal-Wallis test here. Okay, to ask whether the medians of the hydrocarbon values differ by the 5-year groups, and the result here is the rank sum test. We have a chi-square statistic of 31 and the p-value of 0.000002, which is less than 0.05. So there's some evidence here that, in fact, the median hydrocarbons differ over the years. All right. Let's see. So now I want to find the comments in the text that I want to say. Okay, that's fine. In fact, if I page up for a second, on the log scale, these plots, we're in a situation now where maybe look at the symmetry, right? These distributions are much more symmetric than they were before, and perhaps it would be fine to do a standard analysis of variance. And here is the analysis of variance on the log scale. We reject the null hypothesis at almost the same level of significance as the Kruskal-Wallis before. In fact, here is the Kruskal-Wallis result also on the log scale. And one thing to notice here, even though we looked at the log scale here and the original scale before, we have the same chi-square statistic, we have the same p-value. And that's because the Kruskal-Wallis test is performed on the ranks of the data. And one thing that doesn't change when you compare the data from one scale to another are the ranks, right? We have a monotonic transformation here, the log transformation. It's 1-to-1 and monotonic, meaning that if one value is larger than another on the original scale, after the log, that same value is still larger than the other value, right? All the values maintain their order. And so the ranks, the rank of this observation, for example, in the bottom right, is the same regardless of what scale these data are on, providing that the transformation was 1-to-1 and monotonic. So that means that we have the same result. So what does that mean overall in using the Kruskal-Wallis test? Well, the main, let's see, do I have two? Okay, I was looking for the text. I have some text here that says the thing that I want to say. I just can't find it. The point is that if you can find a transformation where the model assumptions, paging up, are satisfied in that the distributions have the same shape over the populations, but just differ in their centers, if that assumption can be met through a particular transformation, then the analysis that is given by Kruskal-Wallis holds regardless of what scale you're on. Because we're looking at inference about the median, the center of the data, that median is in the same position in terms of the observations regardless of what scale you're on. So we found that the log transformation gives us model assumptions that are roughly satisfied. Therefore, the analysis results of the Kruskal-Wallis, if I scroll down just a little bit, on the log scale, those results hold also on, if I page back up, they also hold on the original scale. Okay, so that is the main point of the discussion for this example. So let me scroll on down. All right, there's a little bit more content here, which I'll allow you to read on your own. All right, let's look at a second example. Hodgkin's disease. So I actually have a lot of research you'll find on my CV on Hodgkin's lymphoma in children, and this is a similar type of study. So here we have 3 types of samples. These samples are for different people, and we're going to ask about their Hodgkin's disease status, whether they're normal controls, so they don't have Hodgkin's disease, whether they have active Hodgkin's disease or inactive Hodgkin's disease. And clinicians will be able to help identify these 3 groups of people. Okay, so we want to know, let's see what the values are, whether the plasma levels are the same over these 3 groups of patients. So here are the data. I'm putting it into HD for Hodgkin's disease. We also have different numbers of observations, so I've made the data rectangular with NAs, melted the data into long format, and so we have the patient groups, and then we have the plasma levels as the 2 columns in the data set. Oh, the last thing I forgot to note last time is in the melt function, we can actually remove the NAs when we melt the data. So all these NAs end up disappearing in the long data. All right. Once again, those didn't show up. All right, so those would be the summaries. Yeah, same thing here. That's a nuisance. Well, you can, as always, this R code is on the website, and you can run it, and you'll get all the summaries. So I would have liked to compare whether the variances are the same over these groups, but we'll be able to understand that through some plots. So here are the plots for the levels based on the 3 patient groups. And as we look down here, we see that perhaps we have a bit more spread in the bottom group than the other 2. In particular, maybe you can look at the width of the box, which is the central 50% of the data. It's about twice as wide on the bottom than on the center. If you decide to take a log transform of the axis, these actually look much more similar in their spreads, the main difference being the location. And right away you can see, wow, these normal controls and the inactive Hodgkin patients look really similar and are themselves different from the active Hodgkin's patients. Diagnostically, this may help give you a biomarker to help indicate whether a patient is active or inactive. Okay. All right. So, maybe the thing to mention here, because we found a transformation where we have the same shapes of the distributions, we can apply the Kruskal-Wallis test, and that Kruskal-Wallis test will also apply, the results will also apply on the original scale. So we can set up the hypotheses that eta is the median, and we've got median of the normal controls, the active Hodgkin's, and the inactive Hodgkin's disease patients. We're asking whether the medians for those three groups are equal versus at least one pair is not equal. And the Kruskal-Wallis test indicates, in fact, the p-value that there's a difference between these three groups. And finally, we want to know which pairs differ. If I page up for a second, it's pretty obvious by the eye what the differences are. Okay, and so we'll seek to confirm what we observe through our follow-up pairwise tests. Now, when we performed the standard analysis of variance in Chapter 5, and we rejected the null and found that there were some pairwise differences, our follow-up pairwise test was a two-sample t-test, because we had the normality assumption met, and we continued to use that normality assumption in the pairwise tests. In this case, our Kruskal-Wallis assumption is that our populations have the same shape of the distribution, and when we reject the null that the medians are different, then we have a follow-up two-sample test, and the two-sample test we're going to use is the Wilcoxon-Mann-Whitney test, which also assumes that pairs of populations have the same distribution. And so our pairwise two-sample tests are the Wilcox test. So here I'm putting in for the normal controls versus the active Hodgkin's, and I'm going to construct a confidence interval, and notice my confidence level, 0.9833. I got that using the Bonferroni correction to control for the family-wise type 1 error rate. And what I did is I've got the type 1 error rate that I want of 0.05, and I'm going to divide by the number of pairs of tests that I'm conducting, or the number of tests that I'm doing between pairs. So I have three groups, therefore there's three pairs that I'm performing tests on. That gives us a 0.0167 alpha level. Therefore, the complement of that for not a 95% interval now, but a 98.33, that's 1 minus this, is the confidence level that I want. So I'm going to scroll down. We've got the test between normal controls and the actives. And I'll just summarize these as we go. Here we found a difference. For the normals versus inactives, we do not have a difference. And finally, between the actives and inactives, we also have a difference. Now, all these pink warnings, we always want to read this, but this is because we have ties in our ranks that are being computed. So we can't have exact p-values, but we have approximations, which are just fine. All right. Finally, a summary of what we saw. We have, if we sort active, normal controls, and inactive by their medians, this is the ordering, and the lines indicate groups that are not statistically different. The normals and inactives were not different from each other, but were both different from the active groups. All right. Great. So that finishes analysis of variance. I'm going to go back to a previous example in this discussion of planned comparisons. So it is sometimes the case that a priori, that is before you observe the data, You've got certain populations that you're going to compare through an analysis of variance procedure. And if you reject the null that there's at least one pair that are different, a priori you have certain pairs that you want to compare. So these are planned comparisons. Unplanned comparisons are where you just test every pair of population means or medians to see if they're different. But in this case, before we see the data, we actually know what comparisons are of interest, and we're only going to perform those comparisons. This is a real advantage, especially when you have many populations and when you only have a few planned comparisons that you care about. One natural example is when you have, say, a baseline condition, sort of control condition, and then you have a bunch of treatment conditions. And perhaps you don't want to know the difference between the treatments, but you only want to know which treatments are different from the baseline. Okay, so if, say, you had one baseline or control condition and 5 treatments. So if you want to do every pairwise test, that would be 15 comparisons. That's, when you're doing Bonferroni, that's 0.05 divided by 15. It's a really tiny threshold for significance. Whereas if you only care about whether the 5 treatments are different from the control condition, then you only have 5 pairwise comparisons to do. That brings the alpha level from 0.05 down to 0.01, and that's much more manageable. So whenever you have actual a priori planned comparisons beforehand, you should always use those in favor of the blind compare everything strategy. All right. Amazing. Just the example I gave is exactly what is done here. Okay, so that control for 15 gives an alpha level of 0.003, but if you just do the 5, you get 0.01. Okay. All right, so let's go back to the admissions data that we saw at the beginning of this chapter. And in this case, let's ask whether the medians for cars in consecutive samples are identical. Okay, so that means we're only comparing the oldest to the next one, and so on, each of the consecutive pairs. So now we only have 4 comparisons rather than the 10 that we would have had. That means our alpha level, instead of being 0.005, is 0.0125. All right. So here's all the Mann-Whitney tests. I was sort of hoping that I had a summary at the end. All right. So let's see which pairs here are different. The 2 oldest groups are not different. The second 2 are. So when we go from 63 up to 68, 1963 to 1968, yes. From the late 60s to the early 70s, not different. But from the early 70s to mid 70s, there is a difference. Okay. All right. 2 final comments. It's not uncommon for researchers to combine data from groups that are not found to be significantly different. This is often a bad idea. Just because you do not have sufficient evidence to show differences does not imply that you should treat groups as though they are the same. For example, you could imagine having lots of populations you're comparing, say species of birds or frogs, and you've got only 2 or 3 frogs from every population. And with sample sizes that are tiny, whatever you're comparing, you're not going to have enough statistical power to see that they're different. So if you do a bunch of 2 sample tests and see these 2 species of frogs aren't different, let me just group them. These 2 species, and so on, and group and group and group, you end up with a huge heterogeneous group when you should never have combined them. What you really needed was large enough sample sizes to detect the differences that exist. All right. So that's one example or one comment. The last comment is that if the data distributions do not substantially deviate from normality, but we do have spreads that are different across samples, so we have that unequal variance situation from Chapter 5, then we might consider just doing a standard analysis of variance. But when we do our follow-up pairwise tests, we can always use a two-sample test, say t-test, based on Satterthwaite's approximation for the degrees of freedom. So that is a test that allows us to have unequal variances between our two populations. All right, so that completes this section. The last section of this chapter deals with permutation tests, which is one of my favorite types of hypothesis tests when it is appropriate.